Hey guys, so in today's video, we're actually going to cover a lot of ground. We're going to begin with a review of complex numbers. So you might remember from math class, those are numbers with both a real and an imaginary component. And then from there, we're actually going to implement a class in Python that's going to let us handle and represent those complex numbers. All right, and that's going to entail looking into what's called Dunder methods. And you've probably seen these before, but we're going to practice using them, and you'll get to see them in action. So let's begin with just a brief bit of review as to what a complex number is. So it's going to be a number of the form a plus b I. You've got your real and your imaginary component. And if you remember, I is the square root of -1. That's why it's imaginary, right? So let's just go ahead and we'll write a program that can represent these numbers and print them out. And then we'll come back and look at some of the arithmetic operations that you can do on them. So let's open up a new Python window. Here we are. And we'll make our class. So remember, you start with keyword class, and we'll just call it complex. And it's going to inherit from object, so you could write object in these parentheses, but you don't have to. And now we're going to get to see our first Dunder method. Dunder stands for double underscore. So underscore underscore init underscore underscore. So every class that you make in Python is going to have one of these. This is like the constructor, if you're talking about the equivalent in Java. This tells the class how to create an instance of it. Don't forget to put self in here. And if we look at our formula of a complex number here, we have an A and we have a B. So we'll provide an A and a B. And we should save those to our class. So let's just save this, we'll call it complex. Complex 1. Okay. So there we go. We've saved our A and our B. Down here at the bottom, why don't we make a main method? And we'll just create a complex number. And if you've never seen this idiom before, you can run a method like a main method by doing something like this. Oops. So if underscore underscore name underscore underscore equals underscore underscore main underscore underscore, do this. So basically, if we hit F5 to run this in the shell, or if you were to run it from the command line, it will run whatever you have here. And it's good practice to put that inside of a main method so that it's clear what's going on. So let's run this, and no errors. That's exactly what we want to see. That's good. But wouldn't it be cool if we could actually see something printed out of the form a plus bi? So we give a 2 and a 3. So it would be awfully nice if we could see something that looked like 2 plus 3i. So let's try to get something like that working, because otherwise it's going to be really hard to test anything else that we do. So back in our class, we're going to add another Dunder method, the str method. Str stands for string. So underscore underscore str underscore underscore. And it's just going to take self. It's all you want to return. And now we need to give it the string that should print when we print this object. So take a moment, think about that, see if you can come up with it on your own, and then we'll work through it. Okay, so one approach that you could take is to literally just do this. So the string of A, concatenate that, we'll get some space. With the string of b plus I. So let's see if that works. So let me walk through that really quick. I wrote that pretty fast. So we're getting self.a, which we're going to assume, we're not going to do any error handling here. We're going to assume that that is an integer or a floating point number. And we're going to cast that to a string. So that's the first part. Then a space between them so that they're not joined together. Ooh, I forgot the plus. So we're going to have a space, a plus, and then the b component, which once again is going to be another integer or floating point number. It's going to be some number value, and then the I. So let's run it, see what happens. And there we go. So we gave it 2 and 3. We got 2 plus 3i. But this was pretty easy to write, but it's kind of ugly and it's hard on the eyes. Don't you agree? Like if you looked at this in someone else's code, you'd have to scratch your head and be like, okay, what's all this? There's a lot of plus signs, there's some here, it's something there. Instead, why don't we use string formatting? And if you don't feel comfortable with string formatting, that's okay. It's just something you got to practice with. I've got another video on this channel that looks at string formatting. It's specific to Java, but what you learn there is applicable to multiple languages, including Python. So what we'll do is we'll create a string. It can be like a template string that's going to tell us how we want to build these things. So we're going to start with some sort of an integer. That's our A. D stands for decimal, right? Decimal is a type of number. Then we're going to have a plus sign. So a space, a plus, a space. Then we're going to have another number, and we're going to have an I. So that looks like it's of the form A plus BI. The last thing we need to do is fill in these spaces. The %d says save me a space for an integer here. I'm going to want to put an integer in that space. So now we got to provide the integers that we save the space for. So that would be A and B. See how much shorter that is? And you know exactly what's going on. So that's A, and that's B. No nasty concatenation. So let's run this and verify that we get the same thing out, and we do. So there we go, our str method is finished. So what might be a next logical step? So let's say you had 2 plus 3i, one complex number, and you wanted to add another complex number to it. So that's something you think you might want to do in a program that uses complex numbers. Yeah, I would think so. So how do you add these though? Well, you look at the real parts, you add those together, so you got 7. Then you look at the imaginary parts, you add those, you get 5. So here's our answer, 7 plus 5i. So you look at the real parts, add them together, and then you look at the imaginary parts, and you add them together. So let's try to implement that in Python. Can you guess what Dunder method we're going to want to implement here? Okay, so it's going to be double underscore, add, double underscore. And what this will do is enable us to use the plus operator. So just like over here, you can do with ints, and you can do with floats, and you can do with strings, we'll be able to do it with complex numbers. So we can do like C1 plus C2, where they're both complex numbers, and we'll get a complex number back. That's going to be pretty cool. So what you're going to have to do here is keep in mind that when you're using a plus sign, you've got one thing and the thing you're adding to it. So we have a self, and by convention, we have an other. So other here. we know that we're going to want to return a complex number, just like this. So let's calculate the real part. The real part's going to be self.a plus other.a. Because remember, other is a complex number as well. And then we want the imaginary part, which would be self.b plus other.b. Then we just put real and imaginary here. So here's our a, here's our b, and we've made a new complex number that is self and other added together. We've taken our two complex numbers, combined them, and created another one. So let's create a short little test to see if we can get this to work. So 5 plus 2 is what we did there. So rename this C1. C2 is going to equal complex 5 and 2. C1 plus C2. All right, fingers crossed. Let's see if we did this right. And 7 plus 5i. 7 plus 5i. So now we don't have to think about this anymore. We can give it any two complex numbers, and it will combine them for us. It's pretty nifty. All right, so we can do addition. What's next after addition, do you think? What's the next easiest operator to implement? Well, it's going to be subtraction. All right, and then take 2 seconds, 3 seconds, think about it. What would you guess the name of this method is going to be? It's going to be 3 letters, sub for subtraction. And other than that, it's going to look exactly the same. It's going to take another, and it's going to return a complex number. And we're going to do the exact same thing with the real and the imaginary. So let's look at an example. So let's do the exact same example, actually. Except for this time, instead of adding, let's subtract. So how do you think this is going to work? Well, it's going to basically be the same thing. We're going to do the real part, then we're going to do the imaginary part. So 2 minus 5 is -3, and 3 minus 2 is 1. So 2 minus 5 is -3, 3 minus 2 is 1. So -3 plus 1i. So let's implement that here, and then we'll test it and see if we got it right. So self.a minus other.b, and the imaginary part will be self.b minus, oh, that should say a. So the real parts, subtract 1 from the other, and then the imaginary parts, subtract 1 from the other. Make sure you do them in this order. And then we return a complex number, a new complex number. We're not changing the ones that we started with. That's important. You don't want to change the number that you were given. Because imagine you were doing complex math with these, and you wanted both those values. Maybe you're going to use it again later. You'd be pretty upset if someone modified it or saved over it. So make sure you're creating a new one. And -3 plus 1i, -3 plus 1i. So subtraction is working. So I think what we'll do is we will implement the 4 basic operators: addition, subtraction, multiplication, and division. So let's do 2 more, and then I think we'll have a pretty comprehensive complex number class. So how exactly are we going to multiply these complex numbers? What's that going to look like? So let's just use the same examples, same 2 complex numbers. And let me get this out of the way. I don't think we need that anymore. So we've got 2 plus 3i, and we've got 5 plus 2i. And I've written them like this for a reason. How are you going to multiply them? Well, you can do the FOIL method, right? It's going to be, well, I don't have them written in the FOIL format, but we're basically just going to do FOIL. So 5 times 2, it's 10. I like to do it in a table. It helps me make sure that I keep it all straight. Then 5 times 3 is 15. Don't forget your I. 2 times 2 is 4. Got to grab that I. And 3 times 2 is 6. And now we have 2 i's. So we have I squared. So this whole thing is 10 plus 15i plus 4i plus 6i squared. Is the algorithm starting to come clear? It's okay. We'll run through it if it isn't. So here we multiplied both the real parts. Here we multiplied both the imaginary parts. And here we multiplied the first A with the second B. Here we multiplied the first B with the second A. All right, that's what happened. Or vice versa. But yeah, right? And then we're going to add these together. So you're going to get 10 plus 19i plus 6i squared. But hold on. What are we going to do about that I squared? That doesn't fit into our form. Our form is A plus BI. There's no I squareds in there. That's going to break everything, isn't it? No. If you remember from algebra class, I'll just shrink this. I think we might want to look at it again later. If you remember from algebra class, and from the beginning of this video, I equals the square root of -1. So therefore, I squared is the square of the square root of -1. And then these cancel each other out. So I squared is -1. So that's the same thing as -6. Does that make sense? So I squared is -1 because the square of the square root of -1 is -1. So we multiply -1 by the 6 that's in front of this, and then we end up with 10 plus 19i minus 6. So I'm going to get rid of this so we can rewrite it. Let's see, I'm actually going to use this. Let's make the font quite a bit bigger. Okay, we have 10 plus 19i plus minus 6, right? Which ultimately is 4 plus 19i. So I'll walk through that one more time. So we multiplied the real components, 2 and 5, to get 10. Then we multiply the first real component by the second imaginary component, that's 15i. Then we can multiply the second real component by the first imaginary, or, we're vice versa. I guess this was the second one, the second imaginary component by the first real component to get 4i. And then we multiply the two imaginary components together to get 6i squared. And I squared is -1 for the reasons that we just talked about. So when you combine all these together, you end up with a final answer of 4 plus 19i. All right, let's try to code that up. And maybe looking at it in the code, it'll make more sense. So it's just called the mul method, mul for multiply. It's going to be of the same form as the last two that we did. And we're also going to return a complex number of the form real and imaginary. But the steps we're going to take to get there are going to be a little bit more complicated. So we're going to have what we're going to call real one. And that's going to be where we multiply both the real parts together. So self.a times other.b. And that's just the step here. That's 2 times 5. Now the second real part is going to be both the imaginary parts multiplied together. And you're thinking, well, how is that real? Well, when you get both the i's multiplied, you get -1, so the i's fall out. So it becomes real. So that's going to be -1, because that's I squared, times self dot b times other dot b. Well, this should say a. So both the real parts, the imaginary parts. And then we're going to have 2 imaginary components here. So we're going to multiply the first real number by the second imaginary number. Then we're going to multiply the first imaginary number by the second real number. So maybe pause the video, take a moment, look at what I just wrote, and see that this is the same thing as this little square, this little cross that I've got over here. Okay. Then all we need to do is add these components together. And that is the multiplication operation. So let's see if we can get that to give us this. 4 plus 19i. Bingo. And it took quite a bit of work to get this, right? I mean, if we didn't spend so much time explaining and showing our work, we could probably gotten it done in about a minute, 30 seconds, something like that. But now it's just as easy as 12, 4, there we go. Look at that, we just multiplied those in a second. So that's the beauty, that's the reason why you try to understand the problem so that you can code it up, is now that we've understood it, we've dissected it, we've broken it down to an algorithm, the computer can do it for us so much faster than we could before. All right. So hopefully you're still with me. Hopefully you understand what we've done. We've got one more of these operators to do. And this is going to be a little bit tricky. It's going to be a little bit more involved. So let's say you're dividing them. So first, let me clear our little workspace. So we're going to have something of the form 2 plus 3i. That's going to be divided by 5 plus 2i. Get my pen, just like that. Now that looks like it's going to be tricky. How would you solve that? Do you remember from algebra? Well, what we're going to do is you have to multiply it by the conjugate of this thing. The conjugate of a complex number is basically just a fancy way of saying flip the sign that's in the middle. So if you get it in the form a plus bi, the conjugate is just a minus bi. So multiply it by the conjugate over the conjugate. Because remember, anything over itself is just 1. So this is a legal move. This doesn't change the value at all. But what it does do is it removes the I from the bottom. If you'll multiply this out, you'll see. So then what we'll end up with is 2 plus 3i times 5 minus 2i all over 5 plus 2i times 5 minus 2i. And we could multiply these out like we just did, or we could reap the fruits of our labor and just create some complex numbers. So let's say C1 equals complex 2, 3. Well, let's print it out so we can see it, okay. So 2 plus 3i, good. And let's say C2 equals complex 5 minus 2. So just put the minus right in there. Let's print that, make sure we got it right. 5 plus minus 2i. That's the same thing as 5 minus 2i, right? And I'll leave that as an exercise to you if you want to go in and fix that and make it where it says minus 2. That's up to you. Anyway, let's multiply these two things together. So let's print C1 times C2. 16 plus 11i. I'm sure it's hard to read my paint writing. 16 plus 11i. All right, so that's top of our fraction. And what's this bottom part? We need C3 equal 5 plus 2i. So now we're going to multiply C2 and C3. And look at that, there's no i's there, it's 0i. So it's just 29. So effectively what we have here is 16 over 29 plus 11 over 29i. So that's it. You find the conjugate, you multiply the fraction that you've created by the conjugate over itself. You get this. And then here it is, the answer. Then you can put it in the form a plus bi. So let's start by writing a method that will give us the conjugate. Get conjugate. Don't forget to put your self in there. All of these methods in Python need self. And we're just going to return self.a. Oh, we're going to return a complex number, right? Self.a, and then just -1 times self.b. Right? That's the same thing as making a subtraction, or making a multiplication if it was already a subtraction. And we'll write our div method. I think here we actually want true div. If you're interested in knowing why that is, you can read the documentation. There's a lot to it. But just know if you just do div, it might not work. So true div. We're going to return a complex number. And let's just go ahead and start by getting the conjugate. So call it conj. We want the conjugate of the other, because the other is what's going to be on the bottom of the fraction. So what we found is this thing. We got it from this. That's other. So now let's find the top part of our fraction. It's the numerator, right? We're just going to call it top, but that's the numerator. So that's going to be self. And we could do self._a and self._b and all that stuff. But why would we? We've already written a multiply method. So we're just going to do self multiply the conjugate. Nice and simple, right? Let's go ahead and use what we've already done. And then to get the bottom, we're going to do other. times the conjugate. So there we go. And that's going to give us something of this form. So now what we're going to want to do, so bottom is just going to be a real number. We know that. It's not going to have an I because it can't. Because by definition, the conjugate times whatever it's the conjugate of is just going to cancel out the i's and give you a real number. So what we can do is something like that. That might not be good practice, but that's what we're going to do. Oh, we want the real part, though, not the imaginary part. So this returns a conjugate, or this returns a complex number, and we take the real part of the complex number and we say that's the bottom. So in this case, our bottom will be 29. So it's just going to be an integer. Then lastly, what we need to do is find the real part. Well, the real is going to be top dot underscore a divided by the bottom. The imaginary part is going to be top dot underscore b divided by the bottom. And that should do it. So let's try this. 2, 3. We want to make sure we do one that we already have the solution to so we know it works. And let's run it. Ooh, 0 plus 0i. Any idea why that might be? I know why, do you? I'll give you a hint. It's got to do with over here. So what we did when we took the shortcut, well, not really a shortcut, but we made the string formatting, right? D stands for decimal. These are integer numbers. So it automatically rounded these fractions or truncated them, and we got 0. Let's see what would happen if we replaced them with F's. There we go. And let's see if this is some representation of that. Yes. So this is the right answer. It looks like it at least. Yes. So this is the right answer. But that's not very friendly, is it? And we can't just leave that. So is there a way that we can get this to be in a form closer to what we have over here? You bet there is. There's actually probably a couple different ways. We don't want to implement it from scratch, though. We've already done a lot of work. So why don't we just use an import? We're going to import from the fractions module. We're going to import fraction. How exactly does this work? Well, let's look at it in the terminal. So from fractions, import fraction, we're going to make a fraction. So let's just say we got the number 3. So 3 over 1, that's the fraction. But if you print it, you just get 3, so it looks like an integer. That's pretty nice. But what happens if fraction is like 2.5? Now what happens when we print it? We get 5 halves. So 2.5, we get the fraction version of it. And it's not going to give you 3.5, or I guess 2.5 in this case. It's going to give you 5 halves. But I think that's okay for what we want. This is way more legible than what we had before. So let's just make these fractions, because we never set A or B anywhere else. The only time A and B get set is right here in the init method. Yes, you can access them from the outside. Yes, you could change them theoretically, but we've not given any reason why you should have to do that. So I'm going to do it this way. And then here we can just replace these with S's, because fraction is going to return a string. And it should be hunky-dory now. So look at that, 16 over 29 and 11 over 29. But there's one more thing. Is this 11 over 29i, or is this 11/29 times I? The difference might not seem very big because we know what's going on, but imagine you didn't write this program. 11 over 29i is a lot different than 11/29 times I. So we could fix that by just doing this. All right. But that's going to look pretty ugly when we have something like that. Ew. It looked so much better before, didn't it? So what if this is a whole number? We don't worry about the parentheses. We only want to worry about it if it's a fraction. Luckily, the fraction class will help us with that. So let's say if self.b, we really don't care about a, because it's clear if a is a fraction, it's not really messing with anything. But if self._b dot underscore denominator, so that's the bottom part of the fraction, equals 1, well, then we know this is a whole number, so no parentheses. Else, put parentheses around it. Let's see if that fixed it. So we get our parentheses when it's a fraction. We don't get them when it's not. All right, guys. I think that will wrap up this video. We went over quite a few of these Dunder methods. And like I said, there's still some stuff here that you can work on if you want a challenge exercise. Look at a case like this. So let's say you got a -3 here. Why don't you try to fix the string formatting so that you don't have this plus sign in that case? And that'll do it. All right, I'll see you guys in the next video.